Bakir Trubayev. It's K-A-I-R. Is it Kair or Kair? No. M-I-A. Okay. Ben Swanson. This is section 2, right?
Yeah.
Barton Hansen. Oh, these are graded 80 out of 80. So if you have 80, that means 100. So Thomas, David Ortiz.
Close.
David.
Calculator error?
Ismail Randell.
Yeah, I don't know.
Ismail. You're missing it. Okay. Musa O'Neill.
Melissa?
Melissa. Oh, sorry. L and I.
The frequency? I left it in radiation or something.
Okay, Ryan Waldron. Ryan.
Which one did you get?
Ryan.
The part A.
Tyler Laird. Kay Goldsworthy.
Huh.
Joseph Crolino. Ryan Miller.
I got the same thing, 5.6.
Matthew.
And you said use 19.8 for G.
5.612?
Yeah.
That's what I got.
What the hell? Yeah.
Edwin Greenville.
5.8.
What were your values? 6 and 5?
Niquin. Ryan Ford.
So they were the
Jackie
same.
Pake.
What's it supposed to be?
Nick Romano.
I don't know.
Scott Weinhardt.
Okay.
Jonathan Ewan.
Yeah. 3 halves, yeah.
John
Three
McCraven.
halves of the.
Gotta use it.
To 9/8. So mine should be. Sure.
Okay, Gregory Bridges. Gregory.
So much suspense.
Jan Kennedy. Jack
So you will.
Chappie. Jasper Lewin. Jasper.
Okay, 6.
And Andre F. or E. Hard to read. Any Andre? Okay, no.
So 9.
Okay, Victor Carranza.
Because if all the masses cancel,
Greg
then it would be 9G over 8L.
Yeah, that's probably
Okay.
Daisy Ann. Daisy Ann.
I got to hear it and remember the masses.
Nichols Niguez. Not related to.
Whatever.
I
Scooch
remember.
by another one.
Okay, Marcus Strutz.
Missing a lot of people.
Okay, Alex Zimmerman, I guess. Alex Z. Okay. It's written with font 1.5, so it's hard to read, but it's Alex. Okay, John Kulik. John. Anybody whose name I did not read? Oh.
I sent you a PDF of mine.
Oh, you emailed it?
So did
So
I.
could you send me an email? Then I'll send it back to you, because it was graded on that basic thing that
Ah.
you did. Right,
Okay,
so I didn't print it. Okay, so let's see.
But then how are these correct?
They emailed it to me, they scanned it and sent it to me.
Oh,
Yeah.
different.
So they didn't,
Yeah.
they digitized it, so they wanted to save the planet, and I said, you know,
well, I
Okay.
couldn't make class that day, so.
right, you know, for whatever reasons, yeah.
Because you
Okay.
use omega in here. So
Okay,
this
any
was actually
questions?
wrong.
Yes,
Yeah, we both got the same answer on one that we were marked for being close.
right?
We were wondering if you could work through that one, because also later answers depend on that one.
You know, could I take both of them back, and I'll definitely will be happy to go over them, and who knows, you may get the credit back. Yeah, sure, why not? So let's see. All right, any other questions? Okay. All right. So let's see, I guess, yeah, we are going to, I thought we were ahead of the schedule. No, we're just right on schedule. Okay, so I believe last time in this class, we did we derive the magnification factor or not? Maybe not. So basically, let's go back. We were solving for the case that we have damped vibration under harmonic excitation. So we said that this differential equation obviously has two solutions, one homogeneous, one particular, or there's transient and the steady state part. And we were trying to find a particular solution, which we assume, since due to damping, this should be not necessarily in or out of phase with the forcing function. So we have a form like this. Therefore, we need to find these two unknowns. To do that, we substituted this is the assumed solution, substituted back into the equation, and this is what we derive, right? So if you substitute into that, you take the second derivative, so it would be, okay, cosine of omega t minus omega squared a sine omega t minus theta, that's u double dot, plus 2 zeta omega n. First derivative of that, which would be a omega cosine omega t minus theta plus omega n squared times a sine omega t minus theta is equal to f0 over m sine omega t. So we expanded these because we want to find on the left-hand side, rearrange these in a way that we have sine omega t terms and cosine omega t. On the right-hand side, we only have sine omega t. So if we find all the sine omega t coefficients on the left-hand side, those should be equal to f0 over m, and the coefficients of cosine omega t should be equal to 0. So we rearranged that, and we ended up with these two basically equations, simultaneous equations. So if you expand these, which we did last time, I believe we did that, right? Cosine of omega, this knowing that this is cosine omega t cosine theta plus sine omega t sine theta. This is cosine, this is sine omega t cosine theta minus cosine omega t sine theta. So you expand these and do all the multiplications and algebraic operations and whatnot and find all those terms that are the coefficients of sine omega t. They will be this, omega n squared minus omega squared times cosine theta plus 2 zeta omega n omega sine theta, okay? And so this should be equal to, this is the coefficient for sine omega t. So this should be equal to f0 over m. If you find all the terms corresponding to cosine omega t, you get a times omega n squared minus omega squared sine theta minus 2 zeta omega n omega cosine theta, and that should be 0. So these are the terms for cosine omega t. So you have two equations and two unknowns, being a and theta that you want to find. In order to do that, I multiplied this equation by cosine theta, this one by sine theta, and added the two equations. If you do that, you have these two, this is positive, this is negative, will be the same. They cancel out. So here you will have this time cosine squared, this time sine squared. You factor this out. Sine squared plus cosine squared is 1. So you get a times omega n squared minus omega squared equal to this. So if you solve for a that way, you solve for a and theta, you get a is equal to, comes out to be f0 over k times 1 minus r squared, okay, r squared plus 2 zeta r squared, square root of that, which r is the ratio of omega over omega n. So there would be a little bit of mathematics, algebra involved here, which I skipped them. But you can just simply do that. And remember, also, you need to also remember other trig identities, such as cosine of, say, theta squared, which I have even written it down so that I don't forget, as 1 over 1 plus tangent squared, and things like that. So as you do this algebraic operation, you need to use those identities to eventually come up with these two. Okay, so this is the arc tangent of 2 zeta r over 1 minus r squared. So what that means is the steady state response has an amplitude which would be this, and the phase angle that we, considered as one of the unknowns will be this. So let me write these down and compare that with the undamped case. In the undamped case, right, the amplitude of the steady state response was simply f0 over k over 1 minus r squared, okay? And this was, of course, a static displacement, so we defined this function, okay? We call that amplification or magnification factor. And the absolute value of that, or the magnitude of this, okay, we call that frequency response function, okay? in this case, when damping is not zero, the amplitude is this, 1 minus r squared plus 4 zeta squared r squared, or 2 zeta r squared, okay? So this is the magnification factor, okay? Okay, and this is, I'm not gonna rewrite that down, would be your frequency response function. But in this case, everything was just real number, or real variables. But if you look here, what is the frequency, this magnitude of the frequency response function is actually, it is the magnitude of a complex number like this, okay? Okay, so in this case, the frequency response function is actually the magnitude of this complex function, which we call that complex frequency response function. If you find the magnitude of this function, that would be your amplification factor, or the magnification factor. And that's what we are going to study in depth. In vibrations, in the damped vibration under harmonic load, which results in this complex frequency response function, really lays out the foundation for many concepts that we will basically learn and we will be introducing. It's not difficult to see that why the magnitude of this would be this, okay? This is something like this. 1 alpha plus I beta. So a complex number in general has this form, right? Say x plus I b. How do I turn that into this form? I can just multiply this by alpha minus IB divided by alpha minus IB. So you get alpha minus IB divided by, if you multiply these two, would be alpha squared, right, minus beta squared, right, I being -1, okay? So, because this is, if this is A, this is B, A minus B times, A plus B times A minus B is A squared minus B squared, so B squared has I in it, so it becomes this minus that. So in other words, you get a complex number which has actually that form, okay? Minus I times beta divided by alpha squared minus beta squared. So if you consider this as your x, this as your y, you can simply write the magnitude of this complex number, the absolute value of that, which is z, which is x squared plus y squared, the square root of that, or will be alpha squared over alpha squared minus beta squared okay, squared plus beta squared over alpha squared minus beta squared. And if you substitute for alpha, which is 1 minus r squared, and beta, which is 2 zeta r squared, and simplify this, you will see that this is what you will get. Okay, so that is the amplitude for the magnification factor of the response, or this is the quantity that amplifies the corresponding static displacement. Okay. We are going to focus on this and again make some observations as I did last time. Remember, we had 6 observations. We are going to focus on this and make almost the same number of observations. Any questions? Because it is very important to understand the behavior that this magnification factor or the frequency response function has in the case of damped system as compared with the undamped system. So I will start with, basically similarly with, the same similar observations. I call them observations. So what I'm going to do, I'm going to look at this function, HR, which is 1 over 1 minus r squared plus 2 zeta r squared, square root of that, okay? So let's make a first observation. If you plot this curve, this is what you will see. If you plot R and HR, obviously, if zeta is equal to 0, which is the first observation, you see that this function becomes what you had before. Represents the frequency response function of an undamped system. That is, at R is equal to 1, you get infinite amplitude or the resonance, and then as the R increases, okay, you reach a value R is equal to the square root 2, that at that point also the dynamic response will be equal to the static response, because this will be 1 again. But beyond this ratio, as we discussed last time, the maximum value or the value of the dynamic response is always less than the corresponding static response, okay? So anyway, for zeta equal to 0, that's what you will be getting. But now let's first look at how this curve in general differs from what we had in undamped case. In the undamped case, this was only a function of one variable, R. But in the damped case, this is now a function of 2 variables, both R and zeta. So in other words, the behavior of this plot changes as a function of both. So I'm going to first look at this qualitatively, and then, of course, I'm going to prove a lot of stuff and go through the details of that. If you plot these curves as zeta changes, okay, you will see you get something like this. In other words, as zeta increases, you will see the maximum value of this these curves shifts to the left of r equal to 1. In other words, the maximum value will never be at r equal to 1, and we'll see that mathematically why. So as, say for instance, if this is zeta 0.1, this is zeta 0.3, this is zeta 0.4, this is zeta point, say, 55, that's how this peak value shifts to the left of r equal to 1. We will see at y, but for the time being, let's just make the observation. Not only that, these curves will have a value whose maximum, they'll have a maximum value, okay, that always would be between 0 and 1. In other words, the maximum value for those curves that have a zeta up to 0.707, up to that value, the peak value of these curves is between 0 and 1. Once you reach that value of 0.707, okay, and more, larger, so this is say 0.71, this is say zeta is equal to 1, zeta is equal to 3, and so on. The maximum value is always, in fact, at r is equal to 0. What it means is that as you increase the damping, as you can see, the maximum value or the maximum amplitude of the response decreases, right? So it is only for the value of zeta greater than 0 and less than 0.707 for any system that the dynamic response can be, or the maximum dynamic response can be larger than the corresponding static response. This represents the maximum U, right? Steady state U, but U. Because in other words, this multiplied by F0 over K means maximum dynamic displacement, right? And maximum dynamic displacement greater than the corresponding static displacement is only and only possible if zeta is less than 0.707. When zeta exceeds 0.707, there is no way that you can have a dynamic response that is larger than 1, except at r equal to 0, which means system is not vibrating, is a static case, right? So what it means is in order to decrease the effect of dynamic motion, you need to increase the damping, which is not necessarily a good thing, because increasing the damping means waste of energies, generating heat and whatnot. Usually, too much damping is an unwanted thing. But that's the observation we make here. So actually, I should have called that observation number 2. But let's get to much more details of that. Why is it that at this value, we have all these curves below 1, and so on? That's what I'm going to do. Okay, any questions? So I just described this very overall and qualitatively. Now I'm going to get down to the root cause of these. Okay, so what is happening? Okay, what in other words, there's a curve in these plots in your book, which I have sort of enlarged that. You'll see that these are basically the plots for frequency response function of damped systems. So you can check it out in your book. So those are observation number one. I call that observation number one and two, right? So let's look at the reason now. Okay. So I would call that still observation number two, but I'm going to get into the details of that. Why is it that, as I said, the maximum value for zeta less than 0.707 always on the left side of r equal to 1, and why is it also as zeta increases, we have decrease in the value of the amplitude, and not only that, we reach, of course, this sort of the value that is really the boundary between the two cases. So we're gonna look at that. First of all, let's say we want to find this maximum value, right, of this function. This is a function, we want to find its maximum value. What do? Take the derivative, equate that to 0, right? So that's what we will do. And we want to do that with respect to r. So let's say damping is a constant, we'll just take the derivative with respect to r, okay? If you take the derivative with respect to r, okay, and equate that to 0, you find those values of r that you can substitute there and find damping. So if I do that, this is the function that you get. Take the derivative of that, you get r times 1 minus r squared minus 2 zeta squared divided by 1 minus r squared plus 4 zeta squared r squared times, to the power of 3/2 is equal to 0. That's the derivative of that function. So set the derivative equal to 0. Obviously, this cannot be 0. It's only the numerator that you put to 0, okay? So 1 minus r squared minus 2 zeta squared, equate that to 0. To find the values of r that corresponds basically to maximum value of the function, right? So if you set this equal to 0, you have two possibilities, right? Either r is 0 or 1 minus r squared minus 2 zeta squared is 0, okay? If r is equal to 0, right, in order to find, if you look at these curves that we've plotted, okay, we don't know for what value of zeta that r equal to 0 correspond to the maximum value or minimum value, right? Because at r equal to 0, you see these curves have their maximum value, which is here. Whereas for these curves, actually this may be the minimum value. In order to find that, you need to take the second derivative, right? If the second derivative is negative, that means that number that corresponds to the maximum value. If you're talking about basically curvature, right? When the curvature, okay, of a function, okay, if the curvature, which is the derivative of the derivative, is negative, that means the function is ascending. If the curvature is positive, that means the function is descending. So in other words, the second derivative, okay, if it is negative, that corresponds to the maximum value. If this is positive, that means the minimum value, okay? So we need to take the second derivative. If you take that, okay, d with respect to dr of dh dr, in other words, I'm taking the second derivative of that, you will get a very long function. I'm not gonna even write it down. I will be happy to give you that as a handout or whatever. But if you do that, okay, and you will see that this turns out, and you set R is equal to 0, you will see that you get something which is this. Okay? This is what you get for the second derivative. If this is the second derivative, okay, when would this be negative or when that would be positive? It will be positive when, obviously, right, the positive case happens when 2 zeta squared is less than 1, because this is 1 minus this, right? The only way this can be positive is when this is less than 1, or zeta is less than the square root of basically 0.5. And the square root of 0.5 is about 0.707. If zeta is less than 1, less than 0, that means negative. That means 2 zeta squared is greater than 1, so zeta has to be greater than 0.707. So only for those curves that zeta, okay, is greater than 0.707, okay, or equal to 0 corresponds to their maximum value. So when you set the derivative equal to 0, you have two cases. Either this is 0 or this is 0. You want to find if R is 0, does that correspond to the maximum value of those curves or the minimum values? So by going through this, you prove that for R equal to 0, you will get a maximum for any of these curves as long as zeta is greater than 0.707, which is for these curves. So for all those systems whose damping ratio is greater than 0.707, they will never ever get the response, will never ever get to the corresponding static displacement, which is F0 over K. It's only for those cases where zeta is less than 0.707 that you can reach a value of maximum value of the response that is larger than the corresponding static response. But now the question is, where do you get that? In other words, at what value of R you will get that maximum value? Let's look at this now, okay? If you equate that equal to 0, 1 minus R squared minus 2 zeta squared is equal to 0, this is what you will be getting, okay? First of all, we know that R has to be always positive, right? There is no such a thing as R negative. So if R is positive, then, okay, and this is for the case that zeta is always less than 0.707, right? Because we saw that the only case we have a maximum value corresponding to R equal to 0, which was when zeta was larger than that. So the other case this corresponds to the case that zeta is less than 0.707. So if you consider that in here, okay, you have R is equal to basically 1 minus 2 zeta squared, okay? If this is 0, that's what we'll give you, right? Okay? If that is the case, this is the value of R, okay? And zeta, of course, is less than 0.707, let's see what happened then, okay? Since zeta is less than 0.707, this will be always positive. And this is what you get. H of omega, or H of R, would be 1 over 2 zeta. I will just substitute for R, right? This is the value of R. In other words, I'm not going to skip actually a step here. H of R was 1 over 1 minus R squared plus 2 zeta R squared, right? We know R is 1 minus 2 zeta squared. So for this value of R, H of R becomes this, 1 over 2 zeta, if you simplify that, times 1 minus zeta squared. Zeta is less than 0.707. If you square that, is a small number. So this is almost equal to 1 over 2 zeta. This is the maximum value of the function here. This is the maximum value of these functions, okay? So the maximum value of these functions is 1 over 2 zeta, okay? Which is a very nice discovery. As we said, with the damped vibration, one of the objectives is to find the damping ratio in a system. So if you plot the frequency response function, let's say for any system, okay? Okay? If you plot the frequency response function and find the maximum or the peak value of this curve, which you can measure that experimentally, you probably do this in the lab if you haven't done it already. This is that HR max. Okay? If you just plot it, you know this is 1 over 2 zeta. So you can find zeta by just measuring this height. This is another way of finding the damping ratio in a system, which is a lot easier than logarithmic decrement, because frequency response function is a very common tool that you always basically use in undamped system, and you plot these. So one of the advantages of this, or one of the benefits of frequency response function, is you can find the damping ratio in a system. In fact, because as you can, and we in fact give this a name, this maximum value, we give it a name. We call this maximum value equality factor. Okay? Q equality factor. The lower the damping is, this Q would be higher. So we use actually sort of a terminology that the low Q system or high Q system. High Q system means those systems that have low damping. Low Q systems means those systems that have high damping, right? Because if the larger this is, the smaller that is. So low Q system is high damping, high Q system is a low damp system. It's just a terminology that you may come across. This is a low Q system or high Q system, okay? So that's basically some of the things we wanted to study in the harmonically excited systems. And that, I believe, concludes our, at least the coverage of this topic, except that would be a good idea maybe to look at an example or two. in this case as well, which I'll do that next time.